Okay, so good morning, everyone. So the lecture timing is still the same, 8 a.m. until we find any time that works for everyone. Um, so as we discussed at the end of last lecture, we are going to see an application of Menger's theorem. And we know that in a two-connected graph, by definition, any two vertices are joined by two internally disjoint paths. I might be saying internally vertex disjoint, but that's not necessary. It's internally disjoint is sufficient because it just means that the only vertices shared are the ends, and that means that no edges are shared. Right. So I don't need to specify. Um, Good. So we know that any two vertices belong to a cycle, right? That's equivalent to saying that they are joined by two internally disjoint paths. And the question we asked is something similar true for k-connected graphs. And that is actually true. There is a theorem of Dirac from 1952, which says that for any k-connected graph where k is at least 2, you pick any set of k vertices, and there is a cycle containing all of these k vertices. Right? So they participate in a common cycle. Okay. And while for k equal to 2, this just follows from the definition. This does not follow from the definition for greater values of k. So we need to prove this. Okay, so that's our goal for today. Apart from any other things we may do. Okay, good. So the idea is, so the proof idea, I'm going to do it slightly non-linearly. So the proof idea is to go ahead by induction, because every k connected graph is k minus 1 connected, right? So to prove by induction, on k, right? And already it's true for k equal to 2, right? K equal to 2 holds by definition. So let's just think about, we are trying to prove it for k equal to 3. Okay, let's just think about that. So you've got three vertices u, v, w, distinct. You know that there is a cycle through u and v. If w is on this cycle, then you're done. If w is not on this cycle, then you need to find a better cycle. Right? So let's say w is not on this cycle. So here's the idea. Supposing I was able to find two paths from w, and let's say those two paths go like this, then clearly I can modify the cycle to include w, right? Okay. So I'm trying to prove for k equal to 3. But maybe I cannot find two such paths. Maybe I can find paths which are not going exactly to these two vertices, but let's say they are going, there is a path going here, there's another path going here, and there is yet another path going here. Right? This is all hypothetical. Then once again, I can modify to include this stuff, and I'll get a cycle accordingly. Right? I should have used a different color, too late. Okay. So, but again, who is going to guarantee the existence of such paths? And that's where we are going to prove a lemma which tells us that you can actually, rather than finding paths between two specified vertices, you can find what is called a fan. Okay? And we are going to define a fan, and then we're going to prove a fan lemma, and we're going to use it to prove the theorem. Okay? So we're going to think, so this is where we are heading. We are going to take one vertex, because notice that we are trying to prove by induction. So we already have a cycle on k minus, containing k minus 1 of the k vertices. So now we need a cycle containing that last vertex, and we still want the previous k minus 1 vertices. So what we want to do is we want to include that vertex, And so we are going to find paths from that vertex to a certain set of vertices. And that is called a fan. Let me write down the formal definition. Okay. So what is a K-fan? Um, so you have graph G, you have a vertex X, and you have a set of vertices that does not contain X. Okay, so you have this one vertex X. Okay, maybe I should call this X here. And this is the set Y. Okay, so what we are looking for is a family of K pairwise. They are internally disjoint, but in fact their ends are also distinct. So pairwise internally disjoint XY paths. So what I mean here is the X is the start vertex and the terminal vertex belongs to this set. Okay, so I'm using the order to my advantage. Whose terminals in Y are also distinct. Okay, so they all start at a vertex X and then they end up at distinct vertices in the set Y, and they are completely disjoint except for sharing the vertex X. Any two are disjoint except for the vertex X. Okay, so let's say, to make it very clear, P1 up to Pk, V of Pi intersect V of Pj is precisely the vertex X. Okay, and that also means that their edge sets are completely disjoint. Okay, so if k is equal to 5, then your k fan will look like this. They could be just, some paths could be just edges, there is no problem. Okay, so what we will first do is we will establish the existence of a k fan in any k connected graph where you can choose your vertex X and set Y as you like. Okay, so that brings us to what is called the fan lemma. Proposition 9.5, also called the fan lemma. So it's the same setup. G is a k connected graph. X is any specified vertex. And we've got a set Y of size k. Oh, sorry, I'm going to take it at least k. Then there exists a k fan in G from the vertex X to the set Y. Okay. So I want to do the proof in a non-linear fashion. So I want you to assume this lemma for now and prove, we can try to prove the theorem, and then we will see how to prove this lemma. Any questions, concerns? Okay, so let us assume the fan lemma and prove Dirac's theorem. In fact, I would like to mention that it's often useful when you're reading a math book or a mathy book. It's often useful to read things in a non-linear fashion because when I see a technical lemma, at least I don't feel motivated to read the proof of it or to try proving it on my own, which is always better. So I would strongly recommend that when you're reading something, do consider reading it non-linearly at times. So maybe read the, and this is especially useful when you're reading research papers. At least in my experience, it has served me better than reading linearly. Okay, so let's try to prove Dirac's theorem using this lemma. So as I said, we are going to prove by induction on K. And since any K connected graph is also K minus 1 connected, this is going to be really helpful to us because we can just find a cycle using the K minus 1 vertices. And now we will use the fan lemma to include that last missing vertex. So proof of theorem 9.6. Okay, so K equal to 2 holds by definition. Now assume K is greater than 2. Okay, and for the sake of the proof, I'm going to fix the value of K so that it just makes it easier to visualize things. Okay, so let's say we know that the statement is true for up to K equal to 4, and we are trying to prove for K equal to 5. Of course, I would not do this in when I'm writing a rigorous proof, but right now my goal is not to do that. My goal is to illustrate what's going on, right? So let, for the sake of proof, for the sake of discussion, K equal to 5. Okay, so I have a 5 connected graph and I've got 5 vertices. I want to show that all these 5 vertices belong to a common cycle. So um, let's say the set S is V1, V2 up to V5. And the statement is true for 4 connected graphs, right? So by induction hypothesis, G has a cycle containing, I can pick any of these 4 vertices. So I'll pick V1 to V4, right? Say C. Okay, so C is my cycle containing these 4 vertices. So I've got a cycle here. V1, V2, V3, V4. Okay. And if V5 is on the cycle, then there is nothing to prove. So if V5 is a vertex of this cycle, then we are done. So now suppose V5 is not a vertex of this cycle, right? And just to remind you, K is 5, K minus 1 is 4. Okay. So of course the cycle may contain other vertices. We don't know for sure, right? So let's call Y to be the vertex set of the cycle. Okay, good. So there is a possibility that these are exactly the four vertices on the cycle. Maybe it's just a four cycle and it just contains these four vertices, in which case the cardinality of y is equal to k minus 1. Case 1, cardinality of y is k minus 1. In this case, it's 4. Can anyone suggest what I should do now? I want to get a cycle containing v5 as well and not leaving out any of these four vertices. I want you to use the fan lemma to complete the proof. I have a k-connected graph, I have a vertex v5, and I have a set containing four vertices, v1 to v4. And that's my entire cycle. So I have a cycle containing these four vertices. So can I now use the fan lemma to get a cycle containing all the five vertices? Anyone? Okay, I'll give you a hint. How about we find paths from the vertex v5 to the vertices of the cycle? This cycle has exactly four vertices, v1 to v4, right? If we can find paths from this vertex to these four vertices that are disjoint except for the vertex v5, then I would be done. Supposing I can find all these four paths from v5 to v1, v2, v3, v4, then I'm done. Do you all agree? Then I can just take any two of these paths and extend my cycle using those two paths. Right? So what would this be? This would be a k minus 1 fan. And because my graph is k connected, it is also k minus 1 connected. And so by the fan lemma, which we haven't proved, there is a k minus 1 fan. And I can use this fan to create my cycle with all the five vertices. Right? So that's the argument here. In this case, G is k minus 1 connected because every k connected graph is k minus 1 connected, which implies that G has a k minus 1 fan from the vertex V5, which generally would be Vk, to the set V1 to V4. But in this case, it is just V1 to V4, right? And in the general proof, it would be V1 up to Vk minus 1, right? And now it's clear that we can use this fan. Now it is clear how to construct the desired cycle. Right? Just for the sake of illustration, I could take my cycle to be the cycle as it is, along with two of these paths. Right? Okay. Is this case clear? Are there any questions or concerns? So in this case, we use the k minus 1 fan to get the job done. But our graph is k connected. So we can actually choose a k fan, and that's going to be useful in the next case. So supposing the set Y has at least k vertices. So it doesn't have just these four vertices, v1 to v4. It has some other vertices, let's suppose, right? So let's make a different drawing here. Supposing my cycle has some other vertices like this. Well, now I can't just pick a k minus 1 fan, can I? Let me think about this. Um, right, now the problem is, right, okay. So what's the problem? Why can't we use a k minus 1 fan again? Can someone tell me what's the problem in using a k minus 1 fan this time?
Sir, all could be between two vertices of the cycle, I guess.
Right.
Like all could
So
be between V2 and V3. That's, I think, a problem.
is that a
Like,
problem?
um, wait, no, that's not a problem. Actually, yeah, that's not a problem.
Okay, so then what is the problem? Anand, you mentioned something? Actually, let me make it a bit more complex. Let me put vertices between all of them. So let's say this is
The
V1.
V5 need not be connected to any of the V1 to V4 vertices. It might be connected to some other vertices in the cycle.
Right. Okay. Um, but let's supposing I have V5 going to two of these vertices. This will be good, right? This is a good case, right? If I have two vertices on a common segment, then I would be happy, right? By a segment, I mean between two consecutive vertices in the set V1 to V4. So supposing these vertices appear on the cycle in the order I have drawn, V1, V2, V3, V4. Supposing two of my paths in the fan end on the same segment between V2 and V3. This is actually good news for me, right? Because I can use the cycle and then I can use these two paths to include the vertex V5,
Yes, but in
right?
all other cases, we may not be able to find the cycle.
Yes, exactly. So what could happen if I take a k minus 1 fan? What could happen is one path could go here between V2 and V3. One path could go between V1 and V2. One of them could go between V3 and V4. And one of them could go between V4 and V1. I've got k minus 1 paths because I took a k minus 1 fan because I'm trying to use the argument of the previous case to prove this case, right? And I'm trying to illustrate to you why we run into a problem. Because all of these paths can end up on different segments, right? But good news, we can actually take a k fan. We don't have to take a k minus 1 fan. So we are going to take a k fan, and now something is going to help us.
Pigeonhole principle?
Thank you. Yes. So we are going to take a k fan, and because we have k minus 1 segments, at least two paths will end up on the same segment by the pigeonhole principle, right? And because they end up on the same segment, we can actually use those two paths to construct a bigger cycle or the cycle containing all five vertices. Okay. So in this case, since G is k connected, G has a k fan from V5 to the set Y. Y is the set of the vertices of the cycle, just to remind you, right? Good. And in this case, note that the vertices V1 up to Vk minus 1, which in our case is V1 to V4, they, I'll just use the word induce a partition of the cycle into four segments, right? Or in general, k minus 1 segments, right? So if you have k minus 1 vertices on a cycle, then you get these k minus 1 segments 1, 2, 3, and 4 between the consecutive vertices, right? And because I'm taking a k fan, at least two paths. So let me call this fan P1 up to Pk. By the pigeonhole principle, at least two of these paths from P1 to Pk end in the same segment. So their terminals are in the same segment, right? So what happens is you get two paths that have both ends in the same segment. And I don't care where the other paths go. And in this case, I can construct my cycle as I'm showing now, but I won't write this detail down. You can figure it out for yourself how to write it. Right? So you take all of this stuff and then you take these two paths. Okay? Um, say P1 and P2. Now we may use the cycle C, P1 and P2 to construct the desired cycle containing all of the k vertices that we chose. Okay? So is it clear what happened in this case? Okay, good. So in both cases, we are able to construct a cycle containing the last vertex, right? And so we are done. We have a cycle containing all of the k vertices. Okay, so we assume the fan lemma. So, well, let us not assume it, let us prove it. But again, I'm going to introduce a statement that we will need to prove. And in this case, you will prove it yourself. Okay, so we will assume another fact and then prove the fan lemma. Okay. So let's see. So we want to prove the fan lemma, which means we have a vertex x, we have a set of at least k vertices, we have a k connected graph, and we want to prove that there are these paths that are basically disjoint with each other except for the vertex x. Right? We want to find these paths. What we do know is that between any two vertices, we want these k paths. We know that between any two vertices, there are k such paths. Yes, Anand.
So we can add a new vertex in this graph, say V, and then connect that to every single
Exactly.
vertex in Y.
Exactly. So that's exactly where I was trying to, yeah. So what Anand is suggesting by looking at this drawing, I suppose, is that we can just add a new vertex to the graph, connect it to all the vertices in the set that we have chosen, let's say Y, and then we can use the property of k connected graphs. The only issue is that you have to now explain why when you add a vertex and join it to k vertices or more, the resulting graph is still k connected. So that is our lemma 9.3. So the lemma is you take any k connected graph and we are going to add a vertex to this graph and we are going to join it to at least k other existing vertices of the graph. Then the conclusion is that this resulting graph is also k connected. Okay. let H be obtained from G by adding a new vertex and joining it with at least k. By joining, I mean adding an edge from that vertex to those vertices, right? To k distinct vertices um, of G. Okay. Then the conclusion is that this graph H is also k connected, right? So just to give you a, you take any k connected graph, let's say k is equal to 5. You choose 5 vertices or a bigger set of vertices, doesn't matter. And you add a new vertex and join it to all of these 5 or more vertices. Then this graph H is also 5 connected. Okay. So we are going to use this lemma, and this lemma is an easy exercise. You want to use the definition, the alternative definition, rather than, well, you could, I don't know, you could probably also use the one using paths, but the one, yeah, I would suggest using the alternative definition, which is that either it is a complete graph or otherwise there is no set of k minus 1 vertices that form a vertex cut of the graph, right? That is what it means to be k connected. Any vertex cut should have at least k vertices. So if you use this viewpoint, then you can easily prove this lemma. Okay, so I'm just going to say proved, and you can do it. And if you face difficulties, just start a discussion on Piazza. Okay. So now we can use this lemma to prove the fan lemma. So now, so to prove the fan lemma. In fact, I don't think it even makes much sense to write the whole proof anymore. I'm just going to make a schematic diagram and explain what's going on. So in the fan lemma, you have a k connected graph. You have a vertex x and you have a set y with at least k vertices. Okay. So once again, let's say k equal to 5. Okay, it doesn't matter. You could have more than k vertices here. Now I add a new vertex, y here, and join it to all the vertices in the big set y. Okay, so I'm trying to prove something for the graph G, but instead I look at the graph H, which is also k connected by lemma 9.3. And now, by definition of k connectivity, there exists k internally disjoint paths from x to y. Well, if you take the internally disjoint paths, each such path will have to come to a vertex in the set y, and then it will have to go to the vertex y here, right? And the same for any other path, right? So what I could do is I could basically just chop them off at the last vertex, and that will give me a k fan, right? So consider k pairwise internally disjoint paths from x to y, little y, in the graph H. And chop these paths at the penultimate vertex, right? So x is the start and y is the terminal. to obtain a K fan from the vertex X to the capital Y set. Okay? Yeah. Okay, so that proves the fan lemma. The only thing we haven't proved is lemma 9.3, and I repeat that you should try it yourself. Okay? Are there any questions or concerns so far?
Sir,
Yeah, go ahead, Arnav.
for the fan lemma, we also need to consider the trivial case of a complete graph, right? I mean,
Mm-hmm.
like you just said that there will be a y which will be outside, I guess.
Right.
Other than, yeah.
Right. So if you assume lemma 9.3, then we are not considering any cases here, because for the proof of the fan lemma, I can just add a vertex, join it to everybody, and that
Okay, okay.
graph is K
Yeah,
connected,
yeah, yeah. That's correct.
right?
That's correct. Yeah.
So the complete graph has to be considered for lemma 9.3 separately.
Okay, yeah, fine.
Yeah. Okay. Thanks. Any other questions or concerns? All right. So if not, then there is a second application of Menger's theorem that we have already discussed, which is to prove the edge version of Menger's theorem. So I want to discuss that, but this you'll be proving on the assignment. You may have already seen this on the assignment. So basically, we are moving on to edge connectivity of a graph, but I'm going to keep this discussion quite brief because it's mostly analogous to our discussion on vertex connectivity. It's very similar. Okay, so let's move on to edge connectivity. Okay, so I'll just give you a quick example. Consider this graph, X and Y. Notice that if you're looking for internally disjoint paths here between X and Y, you cannot get more than one path, right? Any two paths will share this vertex. So P of xy, which is the maximum number of pairwise internally disjoint paths between X and Y, is equal to 1. However, you could get paths which don't share any edge. So you can take this as your one path. In fact, I think this is the only way to do it. No, there are two different ways to do it. Doesn't matter. And you can take this as your second path. Okay. So these are not internally disjoint, but they are edge disjoint. There is no edge that is common to both of them. And that weaker notion brings us to edge connectivity. Right? So you could have two paths that are edge disjoint, but are not internally disjoint. Okay, so that brings us to another definition, which is the local edge connectivity between two distinct vertices, X and Y, is the maximum number of pairwise edge disjoint XY paths. Okay. It's generally denoted by, so basically whenever we go from a vertex to edge thing, we will put a prime. So this will happen multiple times in this course. For vertex parameters, we will generally not use prime. For edge parameters, we will use the prime. Okay. So this is P prime XY. Okay, and it is undefined when x is equal to 1. Okay, and now we can define edge connectivity in exactly the same way as we defined vertex connectivity, right? So k edge connected graph, a non-trivial graph G is k edge connected if for any two vertices distinct, the p prime uv is at least k, right? So you have at least k pairwise edge disjoint paths between any two vertices. So I think if you look at this graph is two edge connected, but it is not three edge connected. Okay. And just for the sake of completeness, we are going to adopt the convention that a trivial graph, which means a graph on one vertex, is zero edge connected and one edge connected, but is not k edge connected for all k greater than or equal to 2. Okay, so that's just convention. Okay, and now we can define the edge connectivity of a graph, which is basically the minimum over all pairs where you look at the p prime uv for each pair. Right? So, or another way to put it is the maximum value of k for which the graph is k edge connected. So, edge connectivity kappa prime of g, because we use kappa for vertex connectivity, is equal to the maximum value of k for which g is k edge connected. And if you think about it slightly harder, you see that this is the same as saying that is the minimum value of p prime uv over all uv pairs. Okay, so far we haven't said anything very non-trivial. Okay, and now remember in vertex connectivity we saw two definitions. One is the definition using PUV, which is the it's basically this exact definition. Instead of P prime, you take PUV, right? And then we saw another definition using Menger's theorem, where we have to make an exception for graphs that are whose underlying simple graph is complete. And for all other graphs, this is the same as the maximum, as it's the same as the minimum size of a vertex cut in the graph, right? So the connectivity, to give you an example, the graph's connectivity is 5 if the if you can't disconnect the graph by removing any 4 vertices, and you can disconnect the graph by removing some 5 vertices, right? And in the same way, you can define the edge connectivity of a graph in an equivalent manner. Instead of looking at the paths between two vertices, you look at the size of a cut between two vertices, except that now we are going to look at edge cuts instead of vertex cuts, right? But we have already seen edge cuts in the graph before, when we were looking at the cycle space and bond space of a graph, right? So we have already gone through this discussion about cuts of a graph. So an edge cut, but generally I just call it a cut. Partial S separates X and Y if X is in S and Y is in S bar, where S bar, to remind you, is the complement vertex set. Or of course, Y could be in S and X could be in S bar, right? So to remind you, you've got a cut, you've got a set of vertices S and S bar, and if X is on one side and Y is on the other side, you can call this an XY edge cut or an XY cut, right? So another way to refer to this is it is simply an XY edge cut or an XY cut. Okay. And so you can ask the question, what is the minimum number of edges you need to remove to disconnect the two vertices X and Y? Right. And that brings us to the local edge cut function of a graph. C prime of X and Y is the minimum number, so the minimum cardinality of an XY edge cut. I'm using edge cut right now because I don't want to confuse you with what we just saw, vertex cuts, right? So if you go back to this graph here, it's quite clear to just look at the drawing and see the minimum XY edge cuts have size 2. For example, these two edges incident at the vertex X. Or you can take these two edges, right? So these are all XY edge cuts of size 2. And the fact that they are of size 2 and that this is the minimum size is not surprising because the graph is two edge connected. So you expect something like Menger's theorem to be true, and that is actually true, as you will be proving on the assignment. So what is clear is that if you have got P prime edge disjoint paths, then from each path you must remove at least one edge. And so the size of a cut has to be at least as big as the number of paths, right? So P prime xy is less than equal to C prime xy because any cut has to use at least one edge from all such paths, from each path. So you get this inequality, and then you get theorem 9.7, which is Menger's theorem for edge version. It states that this is not an inequality, but this is actually equal. For any graph G and distinct xy in the vertex set of G, P prime xy is actually equal to C prime xy. And you will be proving this on assignment 2 using theorem 9.1, which is Menger's vertex version. Okay. Good. Quick corollary, and that will be the end. I'm already over time, sorry. A quick corollary is that for a non-trivial graph, notice that here you don't need to make an exception for the complete graphs. It turns out to be slightly cleaner than vertex connectivity. The edge connectivity is the least integer K for which G has a K cut. Maybe I should say separating, because the empty set is also a cut of the graph as per our definition. So I need to make sure that we don't allow the empty cut. So you must separate two vertices. Separating two vertices, two distinct vertices, X and Y. Okay. Yeah. So I think this is all I want to mention for now. There is one more thing. Okay. So also on assignment 2, you will be proving the following inequalities. For any graph G, the connectivity of the graph is less than equal to the edge connectivity of the graph, which is at most the minimum degree of the graph. So this here is the minimum degree uh, among all vertices. Okay, so that's basically all I want to tell you about edge connectivity. The rest you will be finding out on the assignment yourself. And from tomorrow, I want to focus on a special class of graphs called three connected graphs. They will play an important role in planarity, which is our next module. So we will be spending a full week maybe on three connected graphs, and we will see some very interesting theorems. And in the next module on planarity, we will put them put them to use. Okay. All right. Anyways, are there any questions or concerns? I'm here for another 4 or 5 minutes, so please feel free to ask anything. Sorry, the edge connectivity part is a bit rushed, but that's because we spent a lot of time on vertex connectivity, and it's a very analogous discussion. So I didn't see the point of boring you with analogous details once again. Okay, no questions or concerns? All good? Okay, so I'll stop recording.